So our first two units we've covered so far, we covered whole numbers and an introduction to variables in Unit 1. Last unit was dedicated towards fractions and factoring and dealing with common factors and common multiples and stuff like that. This unit, we're going to deal more with algebra and variables, but we're going to deal along with decimals. So this unit is about decimals and algebraic numbers. Now we have worked with certain algebraic numbers so far, dealing with 5x plus 7x, knowing that we can combine those because they have the same name. We can add those. We combine the counts. 5 plus 7 is 12. Then we keep that same name of x. I want to take a little bit of time before we get too far into looking at those operations more. And I want to talk about the structure of our algebraic numbers. To do that, I want to review our place values for our integers and whole numbers. So if you recall our place values, this is the ones, the tens, the hundreds, the 1,000s, 10,000s, and so on. Well, we've talked enough about powers and exponents now that we can define these place values exponentially. We have a base 10 numbering system. Of course, the short word for that is decimal. Deci means 10. So our number system is all based on 10. What that is talking about is exponents. Remember, exponents have two parts. We have the base, which is this bottom number, and the power. So what a base 10 number system is it is a numbering system where the place values are exponents with a base of 10. So this is 10 to the power of 0. Remember, anything to the power of 0 is 1. So 10 to the power of 0 is 1. 10 to the power of 1 is the tens place. 10 to the power of 2, that's 100. 10 to the power of 3 is 1,000. 10 to the power of 4 is 10,000. 10 to the power of 5 is 100,000, and so on. 10 to the power of 6 is 1,000,000. 10 to the power of 7 is 10 million, and we keep going. If I have a number like 3,572, we're used to seeing it written just like that in that abbreviated form. And we've talked before about writing it out in that full form or expanded form, where it might be 3,000 and 500s and 7 tens and 2 ones. But we could also, rather than writing out the words for our place values, we could have used those powers. Come on. We could have actually just written this out as, instead of 3,000, is 3 times 10 to the third, and 500 would be 5 times 10 squared. 7 tens would just be 7 times 10 to the 1, which we don't have to write the 1. We just write 10. And plus 2 ones, well, 2 times 1 is just 2, so we can just write the 2. And when we write it out in that form, it looks a lot like, very similar to, our algebraic numbers. You may have 5x to the third plus 7x squared plus 4x plus 9. You can see the difference is here our place values were, ones, then 10, 10 squared, 10 to the third. Here our place values are ones, and instead of 10, it's x. And instead of 10 squared, it's x squared. Instead of 10 to the third, it's x to the third. So our place values, the algebraic numbers are a numbering system. Instead of being base 10, they're base x. Now, pretty much everything else in the numbering system behaves the same, except for a couple of minor differences. The first one is, of course, our algebraic numbers are always written out in this full form. There is no abbreviation for it. You can't write it smaller. The second is there is no carrying in algebraic numbers. In our standard base 10 numbers, we couldn't have more than one digit in each place value. We get up to 9, and if we get any larger, it has to carry over. In our algebraic numbers, we can have more than one digit in a place value. We might have 7x to the third plus 12x squared plus 19x plus 34. You can see each place value can have more than a single digit, can be larger than 9. There is no carrying from one to the next. And then the third major difference is in our whole numbers and integers or base 10 numbers, either every digit is positive or every digit is negative. If I have a negative 328, that means that's a negative 300s and a negative 2 10s and a negative 8 1s. But in our algebraic numbers, we can have each digit positive or negative all on its own. We could have 5x squared, a negative 3x, and a positive 14. Also, kind of similar to whole numbers, it just looks different. If there's a 0 in a place value, a lot of people don't realize it, but if I have a number like 7,048, we have that 0 in that place value to hold that place so that we know that this is 7,000s and not 700s. But if we write that out in expanded form, we would not include that 0. This would just be 7,000s and 4 10s and 8 1s. We would leave out that 0 hundreds, even though it really is there. When we have the place values written out, we don't need to put the 0 in there. It's implied that if you don't see any hundreds written out, there's 0 hundreds. Similar with the algebraic numbers, we might have something like 7x to the third plus 2x plus 19. What's noticeably missing there? We go from x to the third to x, don't we? There's an x squared missing there. It is implied that it's there. This is 7x to the third plus 0x squared plus 2x plus 19. We don't write that 0x squared in there because we don't need it. It has no value. However, when we go to do any operations with it, we need it in there because we have to account for that place value. So we've seen some of this before where we're doing operations with these algebraic numbers. But let's take a look. We know that we can only add things when we add or subtract. One, we must have the same name. We can only add or subtract things. We can only combine things with addition or subtraction that have the same name. If they don't have the same name, we can put them together, but we can't actually combine them. And then when we add or subtract, we combine the counts, then we keep the same name. Like we saw up above. I have 8x plus 5x. Do those have the same name? Yes, it's x and x. Well, we combine the counts. 8 plus 5 is 13, and we keep the same name of x. A lot of people will mistakenly try to put x squared there, but we don't need that. We are adding or subtracting. We are just going to keep the same name. Nothing to combine. How about if I have 7x squared plus 5x? Can I combine those? No, that is simply going to become 7x squared plus 5x. Now, we've talked a little bit about math grammar so far, about how when we're writing if there's more than one variable on an item, we write them alphabetically. Another thing that we do it all the time, but we don't notice it, is something called descending order. What descending order is from largest power to smallest. When we write any of our numbers, if I look back up here, you'll notice this is the largest power of 10, 10 to the third, then 10 squared, then 10 to the 1. And technically, this is times 10 to the power of 0. So we're going from largest power down to smallest power. Same here. This was x to the third, x squared, x to the 1, x to the 0. All numbers, by the way, no matter what base we're using for place values, will have a ones place because anything to the power of 0 is 1. Some of you, if you go on to computers, computer science, any sort of the IT programs, you might see binary numbers, where it's base 2, or octal numbers, where it's base 8, or hexadecimal, where it's base 16. But there will always be a ones digit no matter what the base of those place values is. Okay, yes, so here we cannot combine those because x squared and x is a different name, different place value. As we've seen, it wouldn't line up even if we were adding numbers. What if we had 11x to the 5th y squared plus 3x to the 5th y squared? Can I combine those? Yes, because they're x to the 5th y squared. They're the same. So what do I get? Perfect. I am adding, so I have the same name, so that means I can combine them. So I add the counts, combine the counts, 11 plus 3 is 14, and I keep the same name. X to the 5th y squared just stays x to the 5th y squared. How about this one? When I go to add those, what do I get? Perfect. 7x to the 3rd y plus 5xy to the 3rd. Those are not the same name. They both have an x and a y, and they both have a power of 3. But here it's x to the 3rd y. Here it's x, y to the 3rd. The power is on a different variable. Those are different names. Now, we just talked a little bit about descending order. Which variable do we use to put them in descending order? Here, the x has the larger power, x to the 3rd, and then x to the 1. So that would be descending with x. But y is y to the 1 and then y to the 3rd. Well, usually it's either specified what variable to put them in descending order, or if it's not specified, the variable that comes first in the list, in other words, first alphabetically, is the one that we put in descending order. So since x comes first, we put it in descending order according to x, unless we're told to do a different variable. looking at this, now there's nothing to do here to combine, but there are 3 digits here, 3 terms. That's what it's called. A term is just an individual digit. So the term is the name for a digit in an algebraic number. They are in descending order, going from highest power to smallest. And then there's something called degree. We can have the degree of a term. The degree of the term is just the power on the variable. If there's more than one variable, it's the largest power, or the power of a specified variable. So here, this term is a degree of 5. This term is a degree of 3, and this term is a degree of 0. There you go. It's x to the 0 that makes that. Good. Second, there's a degree of the whole number. It's called a polynomial. And the degree of the polynomial is just the highest degree of any term. So for this whole algebraic number, that whole polynomial, the degree would be, yes, 5th degree. That would actually be called a 5th degree polynomial. That term 5th degree, if we were to get into, if this were more of a college algebra course rather than pre-algebra, if we were to get more into graphing, 5th degree polynomial has a very specific type of curve shape that it makes in the graph. A 2nd degree polynomial makes a specific shape, and so on. So then we've gone over this a little bit before, but let's review some of our operations with these. Adding. If I wanted to add 735 plus 152, I have to make sure I set this up lining up the columns. My ones with my ones, tens with my tens, hundreds with my hundreds. And I start from my right, work my way back to my left in case I have to carry. So at 5 plus 2 is 7, 3 plus 5 is 8, 7 plus 1 is also 8. If I were adding 2 polynomials, 2 algebraic numbers, now the parentheses here are just to separate the numbers. I might have 7x squared minus 3x plus 9 plus 4x squared plus 7x minus 13. The same thing has to hold true. Now it's not ones, tens, and hundreds that I have to line up, but it is the x squareds and the x's and the ones, it's always ones, of course, that have to be lined up. And I add my columns. Now, of course, we got to be careful with our negatives. So we'll start on the right and work our way back to the left just to be consistent with our whole numbers. We start with 9 plus a negative 13, which is what? Here's 0. We got 9 and negative 13. So that would be negative 4. Then next, we have negative 3x and positive 7. So we know the name there is going to be x because we keep the same name. So we've got negative 3 and positive 7, which is going to be positive 4x. Good. Then we've got 7x squared plus 4x squared, which is 11x squared. So there we are. Does that look familiar? No? Okay. Now we'll do some more examples. So let's say we got 5x to the third plus 2x minus 11 plus 2x squared minus 8x plus 2. We have to line this up. Now we go to write this out, however, 5x to the third, what's missing? X squared. So we're going to have to fill in that missing place value. 0x squared plus 2x minus 11. When we're doing an operation or working with these, we have to account for every place value. Then below that, we got to match up the 2x squared with the other x squared. That'll be the 0x squared. The negative 8x goes under the positive 2x. And the positive 2 goes under the negative 11. And we're adding. If you wanted to, you could fill in 0x to the third here as well. But now let's go ahead and combine. So here we've got negative 11 and positive 2. Negative 9, very good. Here we've got 2x and negative 8x. Well, we know the name's going to be x. We keep the same name. Positive 2 and negative 8. Negative 6x. Here we've got 0 plus 2. 2x squared. And 5x to the third plus nothing is 5x to the third. And of course, since this was a positive 2x squared, I put a plus in there to link those together. Subtraction, remember, works the same way. We just have to be extremely careful with our negatives. We can have 7x squared minus 9x plus 3 minus 9x squared plus 2x minus 13. So we go to line this up. 7x squared minus 9x plus 3. 9x squared plus 2x minus 13. But now we are subtracting down each column. So when I'm doing this, I like to write them off to the side. This is 3 minus a negative 13. When you're just looking at it in the columns like that, it's often easy to miss the double negative. 3 minus a negative 13 is the same as 3 plus 13, which is positive 16. And since it is positive, I am going to put a plus in front of it so that it stays linked in my polynomial. Now then this, negative 9x minus 2x, we know the name's going to be x because we keep the same name. It's negative 9 minus 2, which is going to become negative 9 plus a negative 2. At least we can now do our vectors. We got negative 9 and negative 2 makes negative 11. And 7 minus 9, positive 7 minus 9 is negative 2x squared. So we have 5x to the third minus 7x plus 14 minus 3x squared plus 2x minus 5. Now again, when we go to write this out, what do we notice is missing? X squared. So once again, we have to fill in 0x squared. Where does the 3x squared go then? Under the 0x squared. Very good. How about the 2x? Under the 7x. Yep. And the negative 5, of course, under the 14. And we are subtracting down the columns. Once again, we run to negative 14, or sorry, not negative, 14 minus a negative 5, which is 14 plus 5, which would be positive 19. Now here you have negative 7x minus 2x. We know it's going to be x. It's negative 7 minus 2, which is the same as negative 7 plus negative 2. So negative 7 and negative 2 makes negative 9x. Perfect. 0 minus 3, negative 3x squared. And then think of this as 1 minus 0, 1x to the third, or just x to the third. How does that change if we flip things around? Seven x squared plus 11x minus 15 minus 3x to the third minus 9x plus 2. So we write out the first one here. 7x squared plus 11x minus 15. When we go to put the second number underneath it, what do we have to do? Well, yeah, we'll have to put a 0x to the third up top here. So there's something for our 3x to the third to line up with. Now there is no x squared, so we can put in a 0x squared on bottom. And now this is a negative 9x and a positive 2. Negative 9x and positive 2 right there. And we are subtracting down the columns. So negative 15 minus 2. That's a negative 15 plus a negative 2, which is negative 17. Perfect. 11 minus a negative 11x minus a negative 9x. We know the name's going to be x. 11 minus a negative 9 becomes 11 plus 9, so it is 20x. It's positive, so I put in a plus. This next one is easy. 7x squared minus 0x squared. 7x squared. Yes, you subtract 0, it doesn't do anything. This one's a little trickier. 0 minus 3, negative 3x to the third. What do you think so far? Better than a sharp stick in the eye? So you know the comparison. Let's have you guys try a couple. So there's the first one. Okay, who's your second one? I'll have you try those too, and we'll talk about them in just a second. Let's take a look at the first one here. When you write out this first one, 7x to the third plus 2x minus 19, you notice that the x squared is missing. So you have to remember to put in the 0x squared. And then this is adding, so we're just going to add down the columns. Negative 19 plus 11 is negative 8. The next one, we have 2x plus a negative 9x. The name is x. 2 plus negative 9. There's your negative 7. There you go. Okay. Then the next one, 0x squared plus 5x squared. Well, 0 plus 5 is just 5, and it's still x squared. Positive, so we're going to put a plus in front of it. And then 7x to the third has nothing to combine with. We could have put in a 0x to the third here if we wanted to, but we don't need to. How many of you had that one correct? Good. Any questions on that one? Okay. The second one then, or subtraction, the first one we get written in here, and we don't have any issues with that. It's when we go to write the second one that we notice there's a 7x to the third. So we put in a 0x to the third up here to match up with it. It's missing the x squared, so we put in the 0x squared to fill that place. So then once we have it written out, we subtract 3 minus a negative 12, which is 3 plus 12, or positive 15, good. Then here, negative 19x minus a negative 2x. We know the name is going to be x. Negative 19 minus a negative 2 is negative 19 plus 2 is negative 17. Good. And then 5x squared minus 0x squared is 5x squared. 0 minus 7, negative 7x to the third. Now this was a positive 5, so put a plus in there. Any questions? Okay. Hopefully this is a little clearer than it was last time we zipped through it. We've done several of these types of problems. When we multiply, we combine the counts. 8 times 5 is 40. And then we combine each name individually. X to the third times x to the fourth. X to the 7. When we're multiplying exponents with the same base, these both have a base of x. We add the powers. So x to the third times x to the fourth. We take 3 plus 4 is 7, becomes x to the 7th. How about y to the 5th times y? Y to the 6th. Good. We treat that as y to the 1. So it's 5 plus 1 is 6. Well, we've even seen problems like this. 3x squared y to the third times 7x to the 5th y squared minus 5x to the third y. Yeah, we'll call that good enough. And what do we have to do there? Sure. We could write this out as long multiplication. Then, of course, yeah, this has to multiply that and that. But we have that shortcut we've been using, the distributing. So we'll do the 3x squared y to the third times 7x to the 5th y squared. We multiply the counts. What is 3 times 7? 21. Then we multiply the names individually. X squared times x to the 5th. X to the 7th. Y to the third times y squared. Y to the 5th. And then we have to do the 3x squared y to the third times negative 5x to the third y. 3 times negative 5, negative 15 minus 15. X squared times x to the third, x to the fifth. 2 plus 3 gives us 5. And y to the third times y to the fourth. Again, this is y to the 1, so 3 plus 1 is 4. I'm going to have you try one of those just for practice. 2x to the seventh, y to the third, times 5x to the fourth, y to the fourth, minus 8x to the third, y to the fifth. I'll give you a second to multiply those out. So we'll distribute here. 2x to the seventh, y to the third, times 5x to the fourth, y to the fourth. 2 times 5, 10. X to the 11th and y to the 7th. Good. Then we multiply the 2x to the 7th, y to the third, times negative 8x to the third, y to the fifth. 2 times negative 8, negative 16, x to the 10th and y to the 8th. Very good. Okay, any questions on there? Okay. Well, the next step then is what happens when it's two multiple digit numbers, like 5x plus 2 times 3x minus 7. We have shortcuts for this. All of you have heard of FOIL, or many of you have heard of FOIL probably. But you can just set this up and long multiply it, just like whole numbers. You know, just like any other whole number, you're going to multiply, come on, negative 7 times 2, negative 14. Negative 7 times 5x, negative 35x. Now we've multiplied everything on top by this digit, so we're going to move over. When we move over, we have to put in a 0 here. 3x times 2, 6x, it's a positive 6x, so I'll put a plus in front of it. 3x times 5x. 15, I don't know why I put a 3 there. 15x squared. X times x is x squared. And then we can add negative 14 there. Negative 35x and positive 6 is a negative 29x. Then this is 15x squared. Well, we mentioned this shortcut of FOIL. And all it is, remember, F stands for first. So we multiply the first two digits. 5x times 3x. 15x squared. Notice that was one of the results we had over here. O stands for outer or outside. So we do the outer ones. 5x times negative 7. Negative 35x. Notice that was one of our results over here. I stands for inner or inside. So we multiply the two inside ones. 2 times 3x. What's positive? 6x. And then L stands for last. So we multiply the last digits. 2 times -7, -14. Again, notice all of those are results we had over here. It's just over here they're already lined up, ready to combine the ones that could be combined. Here, are we done at this point? Not quite. We have to combine the like terms. So the 15x squared won't change, but we do have to combine the -35x and +6x to make -29x and the -14. So notice we get the same result. This method's a little shorter and quicker. This one, to me, makes a lot more sense. Well, it's time for me to confuse you just a little bit. You knew it was coming, right? What's different here? Different variables, yes. So we go to multiply. Are you guys comfortable with FOIL, or would you rather see it done out with a long multiplication? FOIL? Okay. So we'll do it that way. I can do it the other way too if people want me to after we're done here. So what do we start out multiplying? 3x times 2y, which is 6xy. 3 times 2 is 6. X times y is just xy. What are the next things we multiply? 3x times +7 is going to be positive 21x. 3 times 7 is 21, and we have the x. Next, we would do -5 times 2y, which is -10y. And finally, -5 times 7 is -35. Is there anything we can combine there? No. Because these were not the same variables, there's nothing there that we can combine together. If those were both x's, there normally would be two terms that we can combine. But in this case, we cannot. We're about 2 minutes early for our break, but let's go ahead and take it now. It's 4:18, 4:19 almost. Let's come back at 4:29. I'm going to have you guys try one or two in your notes here quick. (7x minus 3 times 5y minus 2). Should be 5y. 5x. We'll go 5x minus 2. We'll keep that one simple. We'll go over that one in just a minute. So we'll do 7x times 5x is 35x squared. 7x times -2 minus 14x. Then we go to -3 times 5x minus 15x. And -3 times -2 plus 6. What do we combine? -14 and -15 make -29x. We still have the 35x squared and the +6. Any questions on that one? Okay, let's do another one. 2x plus 9 and 3y minus 5. Let me try that one quick. So 2x times 3y, 6xy. 2x times negative 5 minus 10x. Then we go to 9 times 3y, positive 27y. So put a plus in front of it. 9 times negative 5 minus 45 or negative 45, either way. One more for you to try. 3x squared plus 2 and 5x minus 3. Why don't you try that one quick? So we've got 3x squared times 5x, which is 15x to the third. 3x squared times negative 3. Negative 9x squared. Then we go to the 2 times 5x. That is 10x, positive 10x. And 2 times negative 3. Minus 6. Now there's nothing we can combine there, but we should check to make sure, is that all in the right order? And by right order, I mean descending order. Is it from largest power to smallest? It is. X to the third, x squared, x, and then 1s. So that is in descending order. It worked out that way because I had the x to the squared first here. If I had switched that order, well, in this case, it would have came out either way. But that's the only thing you really have to be careful of, is make sure you combine anything you can combine and then put them in descending order. What if it is 2x plus 5 times 3x squared minus 5x plus 4? I want you to give that a shot, see if you can figure out what it needs to do. So it's just some extra steps here, and then making sure we combine what we can. We'll start out 2x times 3x squared. (6x to the third). Now this middle term isn't really accounted for in our FOIL acronym, but we can adjust for it. We go 2x times negative 5x. Negative 10x. 2x, or negative 10x squared, I should say. 2x times 4. Positive 8x. Now I could keep going along here. 5 times 3x squared. Positive 15x squared. 5 times negative 5x. Negative 25x. And 5 times 4. Positive 20. Now I need to combine here. Is there anything combined with the x, 6x to the third? No. Oops. 6x. How about the negative 10x squared? Yes, positive 15x squared, which makes positive 5x squared. How about the 8x? Yeah, there's the negative 25x. They combine to make, there it is, negative 17x. Then we just have the positive 20 by itself. We have done simple division of single-digit numbers. If we run into something a little bit bigger, we've done this as well. We just have to go piece by piece. Each digit, 32x to the 6th divided by 8x. What is 32 divided by 8? 4. X to the 6th divided by x. Think of that as x to the 1, so it's 6 minus 1. 5. So x to the 5th. Very good. Negative 40x to the 4th divided by 8x. So we combine the counts. Negative 40 divided by 8. Negative 5. X to the 4th divided by x. X to the 3rd. 24x squared divided by 8x. Positive 3. X squared divided by x is just x. Negative 56x divided by 8x. Negative 7. Good. Negative 56 divided by 8 is negative 7. X divided by x cancels out. When you're dividing, you subtract the powers. Exactly. So this is thought of as x to the 1. So 4 minus 1 gives you 3. 6 minus 1 gives you 5, and so on. Okay. Now we want to do some word problems. What we're looking at is, again, combining more than one step. So you might have something like Sam is 6 years older than Pat. Kim is 4 years older than Pat. The sum of their ages is 28. Find each age. So we've got 3 people here. We've got Sam, Pat, and Kim. Let's start from the beginning. Sam is 6 years older than Pat. So can I describe one of those in terms of the other? Let's get my system back up here. I'll pause this. So Sam is 6 years older than Pat. That's what that's saying is, if we call Pat's age X, Sam would be X plus 6. Good, 6 years older. Where does Kim fit into this? Kim is 4 years older than Pat. Well, if Pat is X, that would make Kim X plus 4. Good. So now the sum of their ages is 28. So Sam, which is X plus 6, plus Pat, which is X, plus Kim, which is X plus 4, has to add up to 28. Now we can combine these to get X, X, and X makes 3X. 6 and 4 makes 10, and that equals 28. What do we do next? Subtract 10 from each side. 3X equals 18. And then we divide by 3. X equals 6. All done? No, we have to go back and answer the question. X is 6. Well, that's Pat. Pat's age is 6. Sam's age is going to be 6 plus 6, or 12. And then Kim is X plus 4, so 6 plus 4, or 10. Perfect. Now just to double check, if I add those up, do I get 28? Yes, we do. We can also run into a problem like a rectangle is 6 units longer than wide. The perimeter is 76. Find the length and width. So here's my rectangle. Here's my length. Here's my width. We know that the perimeter is 2L plus 2W. We have to get that down to one variable. Can I get rid of the P in here? Yes, I know the perimeter is 76. So I'll be able to replace that with 76. I have to get rid of either the L or W. Well, it's 6 units longer than wide. So if I keep W for the length, or the width, the length is going to be W plus 6. 6 units more. So then over here, 2L, 2 times L is going to be 2 times W plus 6 plus 2 times the width. Now we have to solve this. We see parentheses there, so that means there's something we need to do there first, which is multiply by the 2. 2 times W is 2W. 2 times 6 is 12. Then we still got the plus 2W here. What can we combine next? 2W and 2W makes 4W plus the 12 yet. And then subtract 12 from each side, so 64 equals 4W. And then divided by 4, 16 equals W. What do we need to do with that? The width is 16. I still need to find, perfect, 16 plus 6 is 22 is the length. The length of a rectangle is 4 times the width. The perimeter is 190. Find the length and width. I'm going to give you guys a few minutes to try this in your notes. So we draw the rectangle. We got width and length. Which one are we going to write in terms of the other? There you go. Length equals width times 4, or length equals 4W. So our perimeter formula, P equals 2L plus 2W, becomes, do we put anything in for P? 190. Do we put anything in for L? Perfect. We replace the 2, instead of 2 times L, it's 2 times, in parentheses, 4W. Plus, how about the 2W? That's just 2W. Then what? 2 times 4W is 8W. And then 8W and 2W makes 10W. And then divide by 10. 19 equals W. Then what? The width is 19. 4 times 19 is 76 is the length. There's no quiz due today since there was a test last class, but there is a new homework that is due for Thursday's class. For those of you planning ahead, there will be a new quiz after Thursday that'll be due on Friday. And there will be new homework. It's just it'll be a week till we have our next class. I know we've got 25 minutes left. I'll hang around if you guys want to look over your tests and see if there are any questions you need answered right now. Otherwise, I will have a little bit of time on Thursday to answer questions on the test too.